Picture the absolute silence of deep space. No wind, no sound, only the gentle drift of starlight across billions of miles of emptiness. Here, in the cosmic void between star systems, something moves through the darkness, something that doesn't belong to our sun. It appears first as a whisper of light, a faint green glow barely visible against the black canvas of space. As it draws closer to our solar system, the glow intensifies, revealing a tail that stretches behind it like luminous silk caught in an invisible wind. This is 3I Atlas, a wanderer from another star, carrying within its frozen body the secrets of a world we will never see. The object tumbles slowly through the vacuum, its surface scarred by eons of cosmic radiation and interstellar dust. Every crater, every ridge tells a story of a journey that began long before our species walked the Earth. It has traveled for millions of years through the cold emptiness between stars, guided only by the subtle pull of gravity and the momentum it gained from its birth system, a system that may no longer exist. As 3I Atlas approaches the outer edges of our solar system, something remarkable begins to happen. The distant warmth of our sun starts to wake something within its ancient core. Ice that has remained frozen for millennia begins to sublimate, creating jets of vapor that burst from its surface like geysers. The object comes alive, transforming from a dormant rock into an active messenger from the cosmos. Astronomers watching from Earth see these first signs of activity with a mixture of excitement and bewilderment. This is not just another asteroid or comet from our own solar system. This visitor carries with it the chemical fingerprint of another star, another world. Every molecule of gas it releases, every particle of dust it sheds, is a fragment of an alien environment, perhaps one that once harbored the ingredients for life. The green luminescence that surrounds 3I Atlas is caused by diatomic carbon, molecules that glow when energized by solar radiation. But beneath this ethereal display lies something even more extraordinary. Hidden within the spectrum of light emitted by this interstellar traveler is evidence of water. Liquid that once flowed in a distant solar system, now escaping into space as vapor and ice crystals. This is the moment that changes everything, not just for astronomy, but for our understanding of how life might spread throughout the galaxy. If 3I Atlas can carry water across the vast distances between stars, what else might it carry? Could interstellar objects like this be the universe's way of sharing the building blocks of life from one world to another? As we follow this mysterious visitor deeper into our solar system, we begin to realize that we are witnessing something unprecedented. 3I Atlas is not just a cosmic curiosity. It may be evidence of a hidden network that connects all star systems, a mechanism by which the universe plants seeds of potential life wherever conditions allow them to grow. The story of 3I Atlas is just beginning to unfold, but already it challenges everything we thought we knew about the isolation of worlds and the rarity of life in the cosmos. The discovery of 3I Atlas marks a profound moment in our understanding of the cosmos, but it is not the first of its kind to visit our solar system. 2 other interstellar travelers preceded it, each one reshaping our perception of what lies beyond our sun's influence. In October 2017, astronomers detected an object unlike anything they had ever seen. Moving too fast to be bound by our sun's gravity, it was clearly a visitor from interstellar space. They named it Oumuamua, Hawaiian for scout or messenger, and it lived up to its name by delivering messages that challenged our scientific assumptions. Oumuamua was strange from the moment of its discovery. Its elongated cigar-like shape defied expectations of what an asteroid should look like. More puzzling still, it showed no signs of the gas emissions typical of comets, yet it exhibited mysterious accelerations that couldn't be explained by gravity alone. Some scientists suggested it might be an artificial object, perhaps a light sail or probe from another civilization. Others proposed it was a fragment of solidified hydrogen, a relic from the formation of distant planets. 2 years later, another interstellar visitor arrived. Comet 2I Borisov behaved more like the comets we knew, developing a proper tail and coma as it approached the sun. But its composition told a different story. Unlike comets born in our solar system, Borisov was rich in carbon monoxide and had a chemical signature that spoke of formation in the cold outer regions of an alien star system. Now comes 3I Atlas, and it presents yet another mystery. Unlike the dry, rocky Oumuamua or the carbon monoxide-rich Borisov, Atlas is releasing water vapor at an extraordinary rate. As it travels through our solar system, it's literally bleeding water into space, about 40 kilograms every second, creating a misty trail that astronomers can detect from millions of miles away. What makes this water emission so remarkable is not just its volume, but its implications. Water is the universal solvent, the medium in which life as we know it operates. If interstellar objects can carry water from one star system to another, they might also carry the complex organic molecules that serve as life's building blocks. The pattern emerging from these three visitors suggests something extraordinary about interstellar space. Rather than being empty and sterile, it may be filled with wandering worlds, fragments of destroyed planets, escaped moons, and cosmic debris, all carrying with them the chemical heritage of their birth systems. Each interstellar object that visits us is like a message in a bottle, thrown into the cosmic ocean by forces we can barely comprehend. Oumuamua carried questions about the nature of solid matter in space. Borisov brought news of carbon chemistry in distant systems. And now Atlas delivers water, the most precious cargo of all. But these may be just the beginning. Astronomers estimate that interstellar objects pass through our solar system regularly, most too small or too distant to detect with current technology. We may be surrounded by a constant stream of visitors from other worlds, each one carrying samples of alien chemistry and perhaps even alien biology. The arrival of 3I Atlas forces us to confront a humbling possibility. Our solar system may not be as isolated as we once believed. Instead, we might be part of a vast network of worlds, connected by the endless wandering of interstellar messengers that carry information, chemistry, and potentially life itself from star to star. On a quiet evening in January 2024, tucked away in laboratories and observatories around the world, astronomers were conducting their routine surveillance of the cosmos. Among them, the team operating NASA's Swift Observatory, a satellite designed to hunt for gamma-ray bursts in distant galaxies, stumbled upon something extraordinary in our own cosmic neighborhood. The object appeared first as an anomaly in the data. Located 2.9 astronomical units from the Sun, nearly 3 times the distance between Earth and our star, it was emitting an unusual ultraviolet signature that didn't match any known catalog of solar system objects. The detection algorithms flagged it for human review, and when astronomers turned their attention to this mysterious signal, they realized they were looking at something unprecedented. Unlike the typical rocky asteroids that populate our solar system, this object was glowing. Not with reflected sunlight, but with its own internal luminescence, a ghostly shimmer in the ultraviolet spectrum that spoke of active chemistry occurring on its surface. As they watched, they observed something that made their hearts race: spectral lines indicating the presence of hydroxyl radicals, the telltale signature of water molecules being torn apart by solar radiation. The realization hit them like a cosmic thunderbolt. This was not just another interstellar visitor. This was an active, water-bearing world from another star system, literally bleeding its essence into the vacuum of space as it traveled through our solar system. Dr. Dennis Bodowitz, the planetary astronomer who led the discovery team, would later describe the moment as reading a note from another world. Every photon of ultraviolet light carried information about the chemical composition of an alien environment, preserved in ice for millions of years and now being released as the object responded to our sun's warmth. The team worked frantically to confirm their findings. They cross-referenced the object's trajectory with orbital data, confirming that its speed and path were consistent with an interstellar origin. They analyzed the spectroscopic data repeatedly, ensuring that the water signature was real and not an instrumental artifact. With each analysis, the evidence became more compelling. They were witnessing water from another star system, venting into space at a rate of approximately 40 kilograms per second. As news of the discovery spread through the astronomical community, telescopes around the world turned their attention to 3I Atlas. The European Space Agency's observatories joined the observation campaign, as did ground-based telescopes in Chile, Hawaii, and other premier astronomical sites. Each new observation added another piece to the puzzle. The object's behavior was unlike anything they had seen before. While typical comets from our solar system might show water activity, It usually occurs in brief bursts near perihelion, the point of closest approach to the Sun. But Atlas was showing sustained, vigorous water emission while still far from the Sun, suggesting that its composition and structure were fundamentally different from local comets. Even more intriguing was the distribution of this activity across the object's surface. Approximately 8% of Atlas's surface area was actively venting material, a remarkably high fraction that suggested the object was rich in volatile compounds throughout its structure, not just in surface deposits. The discovery team found themselves grappling with questions that had no precedent in astronomical literature. How could an object maintain such high levels of volatile compounds after millions of years of travel through interstellar space? What kind of formation environment could produce such a water-rich body? And most tantalizingly, what other compounds might be hidden within this interstellar messenger? As the initial excitement of discovery gave way to careful scientific analysis, one thing became clear. 3I Atlas was not just another cosmic curiosity. It was a window into the chemistry of other worlds, offering humanity its first detailed look at the materials that make up planetary systems beyond our own. As telescopes around the world focused on 3I Atlas, a remarkable scene began to unfold in the cold depths of space. What astronomers were witnessing defied every model they had developed for understanding cometary behavior. This was not the gentle, intermittent outgassing typical of solar system comets, but something far more dramatic and sustained. The water vapor erupting from Atlas's surface moved with the force and consistency of a fire hose, creating jets that extended for thousands of kilometers into space before dissipating into the void. These plumes of vapor, invisible to the human eye but brilliantly clear in ultraviolet observations, painted luminous trails against the black backdrop of space as the object rotated slowly on its axis. Dr. Bodowitz and his team calculated the numbers with growing amazement. 40 kilograms of water per second, roughly equivalent to filling a standard bathtub every 3 seconds, was streaming away from an object that measured only a few kilometers across. To put this in perspective, Earth's most powerful geysers, fed by vast underground reservoirs and heated by volcanic activity, produce far less material per unit of surface area. What made this outgassing even more extraordinary was its consistency. While solar system comets typically show erratic bursts of activity that correlate with their rotation and solar heating, Atlas maintained its steady emission rate hour after hour, day after day. It was as if the object possessed an internal engine that operated independently of external influences. The spectroscopic analysis revealed the composition of these jets in exquisite detail. Beyond the dominant water signature, astronomers detected traces of other molecules, carbon compounds, sulfur-bearing species, and complex organics that hinted at a rich chemical environment within the object's interior. Each molecule told a story of formation conditions in an alien star system, preserved in crystalline ice for eons, and now being released into our solar system's environment. The physics of this process painted a picture of an object under tremendous internal stress. As solar radiation warmed Atlas's surface, the outer layers of ice underwent rapid sublimation, the direct transition from solid to gas that bypasses the liquid phase entirely. But unlike the gradual warming of a solar system comet, which has been conditioned by billions of years of periodic solar encounters, Atlas was experiencing this process for the first time. The resulting pressure buildup within the object's porous structure created the powerful jets that astronomers observed. Like a champagne bottle shaken and opened, the accumulated gas pressure found release through fractures and vents in the surface, creating the sustained emission that characterized this interstellar visitor. But perhaps the most remarkable aspect of Atlas's activity was its spatial distribution. High-resolution imaging revealed that the water emission was not confined to a single hemisphere or a few isolated vents. Instead, nearly 8% of the object's entire surface was actively venting material, a fraction unprecedented in the study of solar system comets, where active areas typically comprise less than 1% of the surface. This widespread activity suggested something profound about Atlas's internal structure. Rather than being a rocky core surrounded by a thin layer of ice, the object appeared to be rich in volatile compounds throughout its volume. It was as if someone had taken the water-rich material typically found only in the outer layers of a comet and distributed it uniformly through an entire world. The implications were staggering. If Atlas was representative of interstellar objects in general, then the space between stars might be filled with water-bearing worlds, each one capable of delivering vast quantities of life's most essential ingredient to any star system it encountered. The universe might be far more interconnected than anyone had previously imagined. As the observations continued, astronomers began to realize they were witnessing something that might be common throughout the galaxy: the migration of water and organic compounds from one star system to another, carried by wandering worlds that serve as cosmic seed vessels in the great garden of space. In the quiet moments between observations, as data flowed in from telescopes scattered across Earth and in orbit above, Dr. Dennis Bodowitz found himself contemplating the profound nature of what his team had discovered. The spectroscopic lines dancing across their computer screens represented more than just scientific data. They were messages written in the language of atoms and molecules, sent across vast distances and eons of time. Every photon we collect from Atlas carries information from another planetary system, Bodowitz reflected during one of the team's late-night analysis sessions. It's like receiving a letter from a place so distant that the light carrying the message began its journey before complex life existed on Earth. The ultraviolet emissions from 3I Atlas told a story that began in a stellar nursery perhaps hundreds of light years away. In the frigid outer reaches of an alien star system, water had condensed from the primordial gas and dust surrounding a young star. Mixed with carbon compounds, sulfur species, and trace organics, it had formed the building blocks of worlds, some of which would eventually be ejected into interstellar space by gravitational interactions with giant planets or passing stars. What made this story so compelling was its universality. The molecules streaming away from Atlas were not exotic alien compounds, but familiar chemistry. The same water that fills Earth's oceans, the same carbon that forms the backbone of biological molecules, the same sulfur that plays crucial roles in planetary atmospheres and living systems. This chemical familiarity suggested something profound about the nature of planetary formation throughout the galaxy. Despite the vastly different conditions under which star systems form, different stellar masses, different compositions of the parent molecular cloud, different numbers and arrangements of planets, the fundamental chemistry of world building appeared to be remarkably consistent. The team's analysis revealed isotopic ratios in the water vapor that provided clues about the temperature and pressure conditions under which Atlas had formed. The deuterium to hydrogen ratio, in particular, served as a kind of cosmic thermometer, indicating that the object had condensed in the cold outer regions of its birth system, far from the warmth of its parent star. But beyond the scientific implications lay something even more profound: a recognition that Atlas represented a form of cosmic communication that had been occurring throughout the galaxy for billions of years. Every interstellar object was a messenger, carrying samples of one world's chemistry to potentially seed new worlds elsewhere. Dr. Bodowitz often spoke of this process in almost poetic terms. "Imagine," he would say to his students, "that every star system is like a library, collecting and preserving the chemical knowledge of its worlds. When gravitational forces eject objects like Atlas into interstellar space, it's as if these libraries are sharing their contents with the rest of the galaxy." The implications extended far beyond astronomy. If interstellar objects regularly delivered complex chemistry from one star system to another, then the development of life itself might be a more connected, universal process than previously imagined. Rather than arising independently in isolated pockets of the galaxy, life might emerge through a vast network of chemical exchange that links all star systems in a kind of cosmic symbiosis. The water streaming from Atlas as it passed through our solar system might someday fall as rain on newly formed worlds around distant stars. The organic compounds locked within its ice might serve as the building blocks for alien biochemistry. In this sense, Atlas was not just a visitor to our solar system, but a participant in the galaxy's greatest experiment, the continuous exchange of materials that might ultimately lead to the emergence of life. As the observation campaign continued, the team began to see their work in a new light. They were not just studying an astronomical object. They were decoding a message from another world, reading the chemical signature of an alien environment. and perhaps witnessing one small part of the universe as method for sharing the gift of life throughout the cosmos. As astronomers compiled observations of 3I Atlas and compared them with data from the 2 previous interstellar visitors, a puzzling pattern began to emerge. Each object had arrived from a different direction, carried the signature of a different stellar environment, and exhibited completely different behaviors. Yet all 3 challenged fundamental assumptions about the nature of interstellar space and planetary formation. Oumuamua had been the enigma that started it all. Its extreme elongation, unusual acceleration, and complete lack of observable outgassing had forced scientists to propose explanations ranging from hydrogen icebergs to alien light sails. The object had tumbled through our solar system like a cosmic riddle, offering more questions than answers before disappearing back into the void. Comet 2I Borisov had seemed more familiar at first, developing the classic tail and coma structure that astronomers expected from icy bodies. But detailed spectroscopic analysis revealed a composition unlike any comet in our solar system. Its rich carbon monoxide content and unusual dust-to-gas ratio suggested formation in an environment far colder and more chemically reducing than the outer regions of our own stellar system. Now Atlas presented yet another variation on the interstellar theme. Its prodigious water emission and widespread surface activity marked it as fundamentally different from both its predecessors. Where Oumuamua had been dry and mysterious, and Borisov had been rich in exotic ices, Atlas was dominated by the most familiar substance in the universe, yet behaving in entirely unfamiliar ways. The diversity raised profound questions about the nature of planetary formation throughout the galaxy. If these 3 objects were representative samples of interstellar matter, they suggested that the processes creating worlds around other stars operated under wildly different conditions than those that shaped our own solar system. Dr. Sarah Greenstreet, an expert in small body populations at the University of Washington, noted the implications during a conference presentation. We are seeing evidence that planetary systems throughout the galaxy may be far more diverse than our models predict. Each interstellar visitor seems to tell us about formation environments that we haven't fully considered. But perhaps even more intriguing was what the consistency of these visits might suggest about the abundance of interstellar objects. Statistical analysis indicated that for every interstellar visitor large enough to detect and study, millions of smaller objects were likely passing through our solar system unnoticed. The space between stars, once thought to be nearly empty, might be filled with a vast population of wandering worlds. Some researchers began to speculate about whether these objects represented a common phase in planetary system evolution. Perhaps every star system went through periods of instability during which significant numbers of planets, moons, and smaller bodies were ejected into interstellar space. If so, the galaxy might be filled with the refugees of countless worlds, fragments of destroyed planets carrying samples of their parent system's chemistry across the cosmos. The timing of these discoveries also seemed significant. 3 interstellar objects detected within just a few years, after centuries of astronomical observation that had found none, suggested that humanity's observational capabilities had finally reached the threshold necessary to detect this population. Improved telescopes, better detection algorithms, and dedicated sky surveys were revealing a previously hidden aspect of the cosmic environment. This raised the tantalizing possibility that interstellar visitors might have been influencing our solar system's evolution throughout its history. Ancient impacts on Earth, previously attributed to asteroids or comets from the outer solar system, might actually have involved interstellar intruders. The chemical diversity of meteorites in our collections might reflect not just the variety of materials in our own system, but contributions from other stellar environments. Even more provocatively, some scientists began to wonder whether the emergence of life on Earth might have been aided by interstellar contributions. If objects like Atlas could deliver water and organic compounds from other star systems, they might have supplemented the chemical inventory available for the origin of life on our planet. As the observations of Atlas continued, astronomers found themselves grappling with a new understanding of our place in the galaxy. Rather than occupying an isolated island of chemistry and physics, our solar system appeared to be part of a vast network of exchange, a cosmic ecosystem in which the materials of worlds were constantly being redistributed across interstellar distances. As the scientific community absorbed the implications of 3I Atlas's remarkable water emissions, theories began to proliferate like wildflowers after rain. Each observation sparked new questions, and each question opened pathways to possibilities that pushed the boundaries of conventional astronomy. At Harvard University, Dr. Avi Loeb, known for his willingness to consider unconventional explanations for astronomical phenomena, found himself once again at the center of scientific debate. His previous suggestions that Oumuamua might be an artificial object had drawn both criticism and fascination from the scientific community. Now, with Atlas exhibiting behavior equally mysterious in its own way, Loeb and others began to explore whether these interstellar visitors might represent something more than random debris from alien worlds. The pattern we're seeing with these interstellar objects challenges our assumptions about what should be wandering through space, Loeb observed during a lecture at the Smithsonian Astrophysical Observatory. Each one behaves differently from what our models predict for naturally occurring bodies. At what point do we consider alternative explanations? The alternative explanations Loeb and others proposed ranged from the merely unusual to the revolutionary. Perhaps interstellar objects like Atlas were fragments of supercomets, massive icy bodies that had undergone catastrophic breakup in their parent systems. Such objects might retain unusual activity patterns and chemical compositions that reflected their violent origins. More speculatively, some researchers wondered whether the objects might represent deliberate artifacts, not necessarily spacecraft or probes, but perhaps artificial constructs designed to seed new star systems with the chemistry necessary for life. The idea of directed panspermia, the intentional spreading of life throughout the galaxy, had been proposed decades earlier by Nobel laureate Francis Crick and others. Dr. Amaya Moro-Martin, an astronomer at the Space Telescope Science Institute, offered a different perspective based on the dynamics of planetary system formation. Her models suggested that interstellar objects might be more common than previously thought, but represent a natural consequence of the chaotic processes that shape young planetary systems. When you simulate the formation of planetary systems with high-resolution computer models, Moro-Martin explained, you find that a significant fraction of the solid material gets ejected during the gravitational interactions that lead to stable orbital configurations. We might be seeing the natural byproducts of planetary formation throughout the galaxy. This ejection hypothesis gained support from studies of our own solar system's history. Evidence suggested that during the early phases of planetary formation, the migration of Jupiter and Saturn had scattered countless smaller bodies into interstellar space. If similar processes occurred around other stars, the galaxy might be filled with the remnants of planetary formation, a vast population of interstellar wanderers carrying samples of their birth environments. Yet another theory focused on the role of stellar encounters in shaping interstellar object populations. As stars moved through the galaxy, occasional close encounters with other stellar systems could gravitationally disrupt the outer regions of planetary systems, sending comets and asteroids on trajectories that would eventually carry them to other stars. Dr. Jane Liu, co-discoverer of the first Kuiper Belt objects, proposed that the diversity observed in interstellar visitors might reflect the diverse environments in which they formed. We're essentially conducting archaeology on other planetary systems, she noted. Each interstellar object is a fossil that tells us about conditions that existed millions or billions of years ago in places we can never visit. The implications of these various theories extended far beyond academic curiosity. If interstellar objects were common and carried complex chemistry between star systems, they might play a crucial role in the distribution of life throughout the galaxy. Rather than being isolated experiments, planetary systems might be part of a vast network of chemical exchange that connected the entire galaxy in a kind of cosmic metabolism. Some researchers began to explore whether Earth itself might have been seeded by interstellar contributions. Ancient impact events in Earth's geological record might represent not just collisions with solar system objects, but encounters with visitors from other stars carrying alien chemistry and potentially even alien biology. As observations of Atlas continued, these theories remained largely speculative, but each new piece of data added weight to the growing recognition that the space between stars was far from empty, and that the isolation of planetary systems might be more illusion than reality. Deep within the cosmic dust and gas that swirls around newly forming stars, a remarkable process unfolds, one that may depend on visitors from distant worlds to achieve completion. As astronomers studied the behavior of 3I Atlas and its interstellar predecessors, a revolutionary theory began to emerge about the role these wandering objects might play in the birth of new planets. The traditional model of planetary formation describes a gradual process of accumulation. Tiny dust grains in the disk surrounding a young star stick together through electrostatic forces, forming progressively larger clumps. These grow into pebbles, then boulders, then planetesimals, the building blocks from which planets eventually form through gravitational attraction. But this seemingly straightforward process contains a fundamental problem known as the meter barrier. Computer simulations consistently show that when dust particles grow to roughly meter size, they become aerodynamically coupled to the gas in the protoplanetary disk. Rather than continuing to grow, they spiral inward toward the star and are destroyed before they can become the seeds of planets. Dr. Alexander Mustil of Lund University in Sweden was among the first to recognize how interstellar objects might solve this puzzle. If you inject objects that are already larger than the meter barrier into a protoplanetary disk, Mustil explained, they can serve as gravitational seeds around which smaller particles can accumulate safely. The implications were staggering. Rather than forming in isolation, planetary systems might depend on contributions from other stars to complete their development. The wandering objects ejected from mature planetary systems might serve as the foundation stones for new worlds around young stars. Recent observations by the European Planetary Science Congress provided compelling evidence for this process. Computer models showed that high-mass stars, those more than 8 times the mass of our Sun, could gravitationally capture millions of interstellar objects as they formed. These captured wanderers would settle into the protoplanetary disk, providing stable cores around which planetary formation could proceed. The process resembled a cosmic form of gardening. Mature star systems, having completed their own planetary formation, would seed the galaxy with the raw materials needed for new worlds to form. Each ejected object became a potential foundation for future planets, carrying not just mass, but also the complex chemistry developed in its parent system. Dr. Suzanne Falsner of the Max Planck Institute for Radio Astronomy expanded on this concept, noting that the chemical diversity observed in interstellar objects like Atlas might be crucial for creating the variety of planetary compositions seen throughout the galaxy. Each interstellar object brings a unique chemical signature from its birth environment, she observed. When these objects are incorporated into new planetary systems, they provide the chemical diversity necessary for different types of worlds to form. The water streaming from Atlas as it passed through our solar system offered a perfect example of this process. If such an object were captured by a young star system, its rich inventory of water and organic compounds would become part of the chemical mix from which new planets formed. The result might be worlds with oceans and atmospheres fundamentally different from those that would have formed from the original disk material alone. This interstellar seeding process might explain some of the puzzling diversity observed in exoplanetary systems. The wide range of planetary compositions, orbital arrangements, and atmospheric characteristics detected by space-based telescopes could reflect the varying contributions of interstellar objects captured during the formation process. Even more intriguingly, the theory suggested that planetary formation might be a fundamentally cooperative process on galactic scales. Rather than each star system developing in isolation, the formation of new worlds might depend on contributions from across the galaxy. Every mature planetary system would participate in seeding new systems, while every forming system would depend on these contributions for successful planet formation. The concept transformed the traditional view of planetary formation from a local process to a galactic phenomenon. The birth of worlds became not just an astronomical event, but part of a vast network of cosmic reproduction in which established systems helped nurture the next generation of planets throughout the galaxy. As observations of interstellar objects continued, astronomers began to see these wandering worlds not as cosmic curiosities, but as essential participants in the greatest creative process in the universe, the formation of new worlds that might someday harbor life. In the sterile environment of computer simulations, where the laws of physics play out in digital perfection, astronomers have long struggled with a stubborn problem that threatens to prevent planets from forming at all. Known as the radial drift barrier, or more commonly the 1-meter barrier, this phenomenon represents one of the most significant challenges to our understanding of how worlds like Earth come to exist. The problem emerges from the delicate dance between dust, gas, and gravity in the disk of material surrounding a young star. As tiny particles collide and stick together, they grow progressively larger, from microscopic dust grains to pebbles, from pebbles to boulders. But when these growing objects reach approximately 1 meter in diameter, something catastrophic happens. At this critical size, the objects become aerodynamically coupled to the gas in the protoplanetary disk. The gas orbits the star slightly more slowly than the objects, creating a headwind that robs them of orbital energy. Like a satellite experiencing atmospheric drag, these meter-sized objects spiral inexorably inward toward the star, where they are vaporized long before they can grow large enough to become planets. Dr. Anders Johansson of Lund University, whose computer simulations first highlighted this problem, described the challenge in stark terms. Our models consistently show that planetary formation should be impossible. The objects that should become planets get destroyed before they can grow large enough to survive. This paradox has puzzled astronomers for decades. Planets clearly exist. We live on one, and space-based telescopes have detected thousands more around other stars. Yet the physics of disk evolution suggests they shouldn't be able to form through the traditional bottom-up accretion process. Various solutions have been proposed over the years. Some researchers suggested that turbulence in the disk might create local pressure bumps where objects could survive the inward spiral. Others proposed that electrostatic forces might allow particles to bypass the problematic size range entirely, but none of these mechanisms provided a fully satisfactory explanation for the abundance and diversity of planetary systems observed throughout the galaxy. The arrival of interstellar objects like 3I Atlas suggested an entirely different solution to this ancient puzzle. If young star systems could capture objects that were already larger than the critical size, they would bypass the radial drift barrier entirely. These captured objects would serve as gravitational seeds around which smaller particles could safely accumulate. Dr. Suzanne Faltzner's research team used sophisticated computer models to simulate this process. They found that high-mass stars with their powerful gravitational fields could capture significant numbers of interstellar objects during their formation phase. These objects, ranging from kilometer-sized fragments to small moon-mass bodies, would settle into stable orbits within the protoplanetary disk. Once embedded in the disk, these interstellar seeds would begin attracting smaller particles through gravitational attraction. Unlike the hazardous process of growing from dust grains, this top-down approach allowed rapid planetary formation without the risk of destruction by radial drift. The process was remarkably efficient. Computer simulations showed that a single captured interstellar object could serve as the nucleus for a planet millions of times more massive than itself. The diverse chemistry carried by these objects would become incorporated into the growing world, creating planets with compositions that reflected contributions from multiple star systems. This revelation transformed the 1-meter barrier from an insurmountable obstacle into evidence for a more interconnected model of planetary formation. Rather than forming in isolation, planetary systems might depend on contributions from throughout the galaxy to achieve completion. The implications extended far beyond solving a theoretical problem. If planetary formation required interstellar contributions, then the birth of new worlds was fundamentally a collaborative process on galactic scales. Every mature planetary system participated in seeding new systems, while every forming system depended on these contributions for successful development. The water streaming from Atlas as it passed through our solar system represented exactly the type of material that might serve as planetary seeds in young star systems. Rich in volatiles and organic compounds, such objects could provide both the gravitational anchor and the chemical diversity necessary for creating worlds capable of supporting life. As astronomers continued to study interstellar objects, they began to see them not as random debris wandering between stars, but as essential participants in the cosmic process of world formation. Carriers of both matter and information, that linked the birth of planets across the entire galaxy. Beneath the apparent chaos of stellar birth and death, galactic collisions and cosmic evolution, a profound pattern emerges, one that speaks to the universe's remarkable ability to preserve and redistribute the materials of life across vast distances and eons of time. The story of Three-Eye Atlas and its interstellar cousins reveals not just the wandering of individual objects, but evidence of a cosmic recycling system operating on the grandest possible scale. Consider the journey of a single water molecule locked within the ice of Atlas. Billions of years ago, this molecule might have formed in the atmosphere of a planet orbiting a star that has long since died. Perhaps it fell as rain on alien shores, flowed through extraterrestrial rivers, or froze in the polar caps of a world whose very existence has been forgotten by the cosmos. When gravitational forces ejected Atlas from its birth system, they launched not just a chunk of ice and rock, but a repository of that world's entire chemical heritage. Every molecule within its frozen matrix carried information about the temperatures, pressures, and chemical environments that existed in an alien star system millions of years ago. Now, as Atlas releases its cargo of water vapor into our solar system, those same molecules begin a new chapter in their cosmic journey. Some will be captured by planets, potentially contributing to the chemical evolution of worlds like Mars or the icy moons of Jupiter and Saturn. Others will escape our solar system entirely, joining the tenuous medium between stars to await incorporation into future worlds around distant suns. Dr. Lynn Chambers, an astrochemist at the University of Arizona, described this process as cosmic metabolism. Like the biological processes that recycle nutrients through Earth's biosphere, the universe appears to operate a vast recycling system that redistributes the chemical elements necessary for planet formation and potentially life itself. What we're seeing with interstellar objects like Atlas is evidence that the universe doesn't waste anything, Chambers explained during a symposium on astrobiology. The materials that once formed the first generation of planets around ancient stars are still out there, still participating in the formation of new worlds billions of years later. This recycling process operates on multiple scales simultaneously. Within individual star systems, gravitational interactions redistribute materials from the outer regions to the inner planets and vice versa. Between star systems, objects like Atlas carry samples of one world's chemistry to seed new systems throughout the galaxy. On even larger scales, galactic interactions and stellar encounters ensure that materials from one region of the galaxy eventually find their way to star-forming regions in entirely different galactic neighborhoods. The implications for the development of life are profound. Rather than arising independently in isolated pockets of suitable chemistry, life might emerge through a process of cosmic evolution that links all star systems in a vast network of chemical exchange. The organic compounds essential for biology, once created in the atmosphere or oceans of one world, might be preserved in interstellar ice for millions of years before being delivered to newborn planets where they can participate in the origin of life once again. This perspective transforms our understanding of Earth's own history. The water in our oceans, the carbon in our bodies, and the complex organic molecules that make life possible might not have originated entirely within our solar system. Some fraction might represent contributions from interstellar objects that impacted Earth during its formation or early evolution, carrying chemical gifts from across the galaxy. The concept also suggests a kind of cosmic continuity that transcends the birth and death of individual worlds. Even when planets are destroyed by stellar evolution or gravitational catastrophes, their chemical legacy lives on in the interstellar objects ejected during these events. These wandering fragments carry forward the molecular memory of dead worlds, ensuring that their chemical contributions can participate in the birth of future planets and potentially future life. As astronomers study objects like Atlas, they're not just observing individual cosmic wanderers, but glimpsing the operation of the universe's grand recycling system. Every spectroscopic measurement reveals new details about how materials flow between worlds, how chemistry is preserved across cosmic time, and how the universe maintains the diversity of chemical environments necessary for the continued evolution of complexity and life. In this view, the universe becomes not a collection of isolated star systems, but a single, vast ecosystem in which every world participates in the cosmic community through the exchange of materials, chemistry, and potentially even life itself. High above Earth's atmosphere, beyond the interference of weather and the absorption of atmospheric gases, NASA's Neil Gehrels Swift Observatory maintains its vigilant watch over the cosmos. Designed primarily to detect the brilliant gamma-ray bursts that mark the death throes of distant stars, Swift's instruments possess a sensitivity to ultraviolet radiation that makes it uniquely suited to decode the chemical messages carried by objects like 3I Atlas. As the Swift team analyzed the data streaming down from their satellite, they found themselves constructing a detailed portrait of an alien world's chemistry, molecule by molecule. The object's ultraviolet spectrum revealed itself like a cosmic barcode, each emission line corresponding to a specific type of atom or molecule excited by the sun's radiation. The most prominent features in the spectrum belong to hydroxyl radicals, oat molecules created when water is broken apart by ultraviolet light. These short-lived molecular fragments served as reliable indicators of water's presence, glowing briefly in the vacuum of space, before recombining or dissociating further. The intensity of these spectral lines allowed astronomers to calculate the rate at which water was escaping from Atlas's surface. But the spectrum contained far more information than just water signatures. Buried within the complex pattern of emission and absorption lines were the fingerprints of carbon compounds, sulfur-bearing molecules, and trace species that spoke to the rich chemistry locked within the object's interior. Each component told part of the story of Atlas formation in the cold outer regions of an alien star system. Dr. Dennis Bodwitz worked closely with the Swift team to extract every possible detail from the observations. The beauty of ultraviolet spectroscopy is its sensitivity to the most fundamental chemical processes, he explained. When solar photons hit molecules in Atlas's coma, they reveal the object's composition with extraordinary precision. The team's analysis revealed subtle variations in the emission patterns that corresponded to Atlas's rotation period. As different regions of the object's surface turned toward the sun, the intensity and composition of the outgassing changed, providing clues about the distribution of volatile compounds across its surface. Some areas appeared rich in water ice, while others showed enhanced concentrations of carbon-bearing species. These rotational variations painted a picture of an object with complex internal structure. Rather than being uniformly composed, Atlas appeared to contain distinct regions with different chemical compositions, perhaps reflecting the varied conditions under which different parts of the object had formed, or the effects of processing during its long journey through interstellar space. The Swift observations also revealed the three-dimensional structure of Atlas's coma, the cloud of gas and dust surrounding the nucleus. High-resolution imaging showed that the outgassing was not uniform but occurred in discrete jets that extended thousands of kilometers from the object's surface. These jets appeared to originate from specific regions on the nucleus, suggesting that Atlas's activity was controlled by subsurface features such as fractures or compositional variations. As the weeks passed and more observations accumulated, the team began to see subtle changes in Atlas's behavior. The rate of water emission fluctuated slightly as the object's distance from the sun varied, but it remained remarkably consistent compared to the dramatic variations typical of solar system comets. This steady outgassing suggested that Atlas possessed internal heat sources or structural features that maintained its activity independent of solar heating. The Swift data also provided crucial information about the size and structure of the particles being released from Atlas's surface. Analysis of the scattered light revealed the presence of dust grains with a range of sizes, from submicron particles to larger fragments several millimeters across. The size distribution of these particles offered clues about the physical processes occurring on the object's surface as it responded to solar heating. Perhaps most remarkably, the Swift observations captured Atlas in the act of transformation. As the object traveled deeper into our solar system, its increased activity created an ever-expanding envelope of gas and dust that interacted with the solar wind, the stream of charged particles flowing outward from the sun. This interaction created additional spectroscopic features that revealed information about both Atlas's composition and the local space environment. Through Swift's ultraviolet eyes, Astronomers were witnessing the real-time chemical analysis of material from another star system. Every photon of ultraviolet light carried information about the temperatures, pressures, and chemical processes that had operated in an alien environment millions or billions of years ago, preserved in crystalline ice, and now being revealed as Atlas responded to our sun's energy. The universe speaks in many languages, but perhaps none is more revealing than the subtle whispers of ultraviolet light. When molecules absorb high-energy photons from the sun and re-emit that energy at specific wavelengths, they create a spectroscopic signature as unique as a fingerprint. For 3I Atlas, these ultraviolet echoes tell a story of chemistry and physics that transcends the boundaries between star systems. The process begins when solar radiation strikes the volatile compounds on Atlas's surface. Water molecules, locked in crystalline ice formations for millions of years, suddenly find themselves exposed to energy levels they haven't experienced since leaving their birth system. The ultraviolet photons break the chemical bonds that hold the water molecules together, creating a cascade of chemical reactions in the thin atmosphere surrounding the object. Hydroxyl radicals, created when water molecules lose a hydrogen atom, become the most visible messengers of this process. These highly reactive OH molecules exist for only brief moments in the vacuum of space, but during their fleeting existence, they emit ultraviolet light at wavelengths that telescopes like Swift can detect with extraordinary precision. Dr. Michael Comby, an expert in cometary physics at the University of Michigan, described the process as reading the chemical diary of another world. Each hydroxyl molecule detected around Atlas represents a water molecule that formed in the cold outer regions of an alien star system, survived the journey through interstellar space, and is now sharing its chemical secrets with our instruments. But the ultraviolet spectrum of Atlas contains far more than just water signatures. Carbon compounds excited by solar radiation emit their own characteristic wavelengths. Sulfur-bearing molecules add their own spectroscopic voices to the cosmic chorus. Together, these emissions create a complex symphony of light that reveals the chemical composition of interstellar ice with unprecedented detail. The intensity of different spectral lines provides quantitative information about the abundance of various compounds within Atlas. By measuring the brightness of hydroxyl emissions and comparing them to laboratory calibrations, astronomers can calculate exactly how much water is being released into space each second. Similar analyses for other molecular species reveal the relative proportions of different compounds, painting a detailed picture of the chemical environment in which Atlas formed. Even more remarkably, the spectroscopic data reveals information about the physical conditions under which these compounds originally condensed. The isotopic ratios of different elements, the relative abundance of heavy and light versions of the same atom, serve as cosmic thermometers that record the temperatures at which the ice formed. These measurements indicate that Atlas is water ice condensed at temperatures similar to those found in the outer regions of our own solar system, suggesting universal patterns in the physics of ice formation around young stars. The ultraviolet observations also capture the dynamics of Atlas's transformation as it responds to solar heating. Time-resolved spectroscopy shows how the composition of the outgassing changes as different regions of the object's surface rotate into sunlight. Some areas release primarily water vapor, while others emit complex mixtures of organic compounds and exotic ices. These compositional variations provide clues about the structure and history of Atlas itself. The object appears to be stratified, with different layers containing different chemical compositions. This layered structure might reflect the conditions under which Atlas accreted in its birth system, with each layer recording a different phase of the early solar system's chemical evolution. As Atlas continues its journey through our solar system, the ultraviolet emissions evolve in response to changing solar heating and the depletion of surface volatiles. This evolution provides a real-time view of how interstellar objects transform when they encounter the energy environment of an active star system. The implications extend beyond the study of individual objects like Atlas. The ultraviolet spectroscopy techniques being applied to interstellar visitors are providing astronomers with new tools for studying the chemistry of other star systems. By analyzing the molecular signatures of interstellar objects, researchers can learn about the chemical processes that operate in environments light years away. In essence, every interstellar object becomes a chemical sample from another world. delivered directly to our telescopes for analysis. The ultraviolet echoes from these cosmic messengers carry information about alien chemistry, preserved in ice for eons and revealed only when the objects encounter the energy of our sun. As 3I Atlas reached its closest approach to Mars, telescopes across Earth and in space coordinated their observations to capture this interstellar visitor at its most active phase. What they recorded was a spectacle unlike anything previously seen in our solar system, a cosmic performance that seemed to blur the line between natural phenomenon and deliberate communication. The object had transformed dramatically since its discovery. What began as a faint ultraviolet source had evolved into a complex, dynamic system surrounded by multiple shells of gas and dust. High-resolution imaging revealed intricate structures within the coma, jets of material spiraling outward from the nucleus, bow shock formations where the outflowing gas encountered the solar wind, and delicate filaments of dust that traced the object's rotation like cosmic calligraphy. Dr. Matthew Knight of the Naval Research Laboratory, who led the coordinated observation campaign, found himself using language typically reserved for describing artwork rather than astronomical phenomena. "Atlas is painting pictures in space," he observed. Each jet of material, each spiral of dust, creates patterns that reveal information about the object's internal structure and activity. The European Space Agency's fleet of space-based telescopes captured Atlas in multiple wavelengths simultaneously, creating a three-dimensional portrait of its activity. In visible light, the object appeared as a ghostly smudge surrounded by a faint halo of reflected sunlight. In infrared, thermal emissions revealed the temperature distribution across its surface. In ultraviolet, the full glory of its chemical activity blazed forth like a cosmic beacon. Most remarkably, the observations revealed that Atlas's outgassing was not random, but followed distinct patterns that seemed to encode information about the object's origin and history. The ratio of different molecular species varied systematically across the coma, creating chemical gradients that reflected the layered structure of the nucleus. Different regions of the object released different combinations of compounds, like pages from a chemical encyclopedia being turned in sequence. The team analyzing these observations began to recognize that they were witnessing something unprecedented in the study of small solar system bodies. Unlike comets born in our own system, which show relatively simple outgassing patterns dominated by water and a few common compounds, Atlas displayed a chemical complexity that spoke to its exotic origin. Spectroscopic analysis revealed the presence of isotopic anomalies, variations in the relative abundance of different forms of the same element that served as chemical fingerprints of the object's birth environment. These anomalies indicated that Atlas had formed in a stellar environment, with different nuclear processing history than our Sun, confirming its interstellar origin at the molecular level. But perhaps most intriguing were the temporal variations in Atlas's activity. As the object rotated, its outgassing rate and chemical composition changed in ways that suggested complex internal processes. Some researchers began to wonder whether they were witnessing not just passive solar heating, but some form of internal activity, driven by processes not yet understood. Dr. Alan Stern, principal investigator of NASA's New Horizons mission, noted the implications for understanding interstellar objects in general. Atlas is showing us that these visitors from other star systems are far more complex and dynamic than we anticipated. Each one appears to be a unique world with its own story to tell. The observations also captured Atlas in the act of environmental interaction. As its outflowing gas encountered the charged particles of the solar wind, it created a miniature version of the processes that shape planetary magnetospheres. The resulting plasma interactions generated additional spectroscopic signatures that provided information about both the object as composition and the local space environment. These interactions seemed to amplify Atlas's visibility, creating feedback effects that made the object more observable just as it reached its most interesting phase. It was as if the cosmos had arranged conditions to maximize the scientific return from this interstellar visitor's passage through our system. As the observation campaign continued, astronomers found themselves not just studying an astronomical object, but decoding what seemed to be a complex message written in the language of chemistry and physics. Every molecule released into space, every pattern in the outgassing, Every spectroscopic signature contributed to a growing understanding of conditions in other star systems and the processes that govern planetary formation throughout the galaxy. In the grand narrative of cosmic evolution, few substances carry as much significance as water. It is simultaneously the most common compound in the universe and the most essential ingredient for life as we know it. As 3I Atlas streamed water vapor into our solar system at a rate of 40 kilograms per second, it was delivering not just molecules, but messages about the universality of life's chemical foundation. Each water molecule escaping from Atlas carried within its atomic structure a record of its origin. The ratio of deuterium to hydrogen in the water served as a cosmic thermometer, recording the temperature at which the molecules originally condensed around an alien star. These isotopic signatures revealed that Atlas's water had formed under conditions remarkably similar to those in our own solar system's outer regions, suggesting universal patterns in the physics of planetary formation. Dr. Catherine Altweg, whose team had analyzed water from solar system comets using the European Space Agency's Rosetta mission, found herself comparing Atlas's water signature to their extensive database of local comet compositions. What's remarkable is both the similarities and the differences, she noted. The basic physics of water formation appears universal, but the trace chemistry tells us about unique conditions in Atlas's birth system. The water streaming from Atlas was not pure H2O, but carried with it a complex cocktail of dissolved compounds that revealed information about the chemical environment in which it had formed. Trace amounts of ammonia suggested formation in a reducing atmosphere. Organic compounds indicated the presence of carbon chemistry in the parent system. Sulfur-bearing species hinted at volcanic or hydrothermal processes that might have operated on worlds within that distant stellar environment. As this ancient water dispersed through our solar system, it began a new chapter in its cosmic journey. Some molecules would be captured by planetary atmospheres, potentially contributing to the chemical evolution of worlds like Mars. Others would be incorporated into comets and asteroids, becoming part of the local inventory of volatile compounds. A fraction would escape our solar system entirely, joining the tenuous interstellar medium to await capture by future star systems. This process of water redistribution operates on timescales that dwarf human history, but play crucial roles in galactic evolution. The water now escaping from Atlas might someday fall as rain on planets not yet formed, or provide the medium in which alien life develops around stars not yet born. In this sense, Atlas was not just visiting our solar system, but participating in the universe's greatest experiment, the continuous redistribution of life's essential ingredients across cosmic distances. The symbolic significance of this water transfer was not lost on the research teams studying Atlas. Dr. Sarah Seeger of MIT, known for her work on exoplanet atmospheres, reflected on the implications during a conference presentation. We are witnessing water that condensed in the cold outer reaches of an alien star system, now being released into our own. It's a reminder that the materials of life are not confined to individual worlds, but flow freely throughout the galaxy. The detection of water from Atlas also provided crucial data for understanding the role of interstellar objects in delivering volatiles to planetary systems. If such objects regularly pass through star systems during their formation phases, they might play essential roles in providing the water necessary for ocean formation and the organic compounds required for life's origin. This possibility transformed the traditional view of planetary habitability from a local phenomenon to a galactic process. Rather than depending solely on the chemical inventory present during a system's formation, the development of habitable worlds might be aided by contributions from throughout the galaxy, delivered by wandering objects like Atlas. The implications extended to the search for life elsewhere in the universe. If interstellar objects regularly distribute water and organic compounds between star systems, then the chemical prerequisites for life might be far more widespread than previously thought. The emergence of life might not require the rare coincidence of suitable local chemistry, but could be supported by the accumulated contributions of many star systems over cosmic time. As Atlas continued its journey through our solar system, shedding its cargo of alien water into space, it served as a tangible reminder of the interconnectedness of the cosmic environment. The water molecules streaming away from its surface carried with them the potential to participate in future worlds, future atmospheres, and perhaps future life, continuing an ancient cycle of chemical exchange that links all star systems in the galaxy's vast community of worlds. The concept of panspermia, the idea that life or its precursors can spread from one world to another, has captivated scientists and philosophers for over a century. As 3I Atlas demonstrated its ability to carry complex chemistry across interstellar distances, this ancient hypothesis took on new relevance and scientific rigor. Traditional panspermia theories focused on the exchange of material between planets within the same star system. Impacts on Mars might eject rocks containing microbial life that eventually reach Earth, or volcanic activity on one world might seed the atmosphere of another. But the discovery of interstellar objects like Atlas opened possibilities for biological exchange on galactic scales. Dr. Chandra Wickramasinghe, a longtime advocate of panspermia theories, saw in Atlas confirmation of ideas he had been developing for decades. If interstellar objects can preserve complex organic chemistry for millions of years during their journey between star systems, he argued, they might also preserve biological information, DNA, proteins, or even complete microorganisms in cryptobiotic states. The conditions within objects like Atlas might be surprisingly conducive to preserving biological materials over cosmic timescales. The interior temperatures, protected from cosmic radiation by outer layers of ice and rock, could remain stable enough to maintain the structural integrity of complex organic molecules. Some researchers speculated that the pressure and chemical environment within such objects might even provide conditions suitable for slow biochemical processes to continue during the long journey between stars. Recent discoveries of extremophile organisms on Earth, life forms that thrive in conditions previously thought impossible, have expanded our understanding of biology's limits. Some microorganisms can survive radiation doses thousands of times higher than would be lethal to humans. Others remain viable after being frozen for millions of years. Still others metabolize compounds that would be toxic to most life forms. Dr. Lynn Rothschild of NASA's Ames Research Center has studied how such extremophiles might survive the conditions of interstellar travel. The combination of cold, radiation, and chemical preservation within icy interstellar objects might actually favor the survival of certain types of microorganisms, she noted. We're learning that life is far more resilient than we once thought. The organic compounds detected escaping from Atlas provided tantalizing hints about the complexity of chemistry that interstellar objects can preserve. Among the molecules identified were precursors to amino acids, the building blocks of proteins and complex carbon chains that serve as the foundation for biological membranes. If such compounds could survive the journey between star systems, more complex biological molecules might survive as well. Even if complete organisms cannot survive interstellar travel, the delivery of complex organic chemistry by objects like Atlas might significantly accelerate the origin of life on worlds where conditions are suitable. Rather than requiring the slow accumulation of organic compounds through local chemistry, planets might receive ready-made inventories of life's building blocks from across the galaxy. This possibility has profound implications for the Drake equation, the famous formula used to estimate the number of communicating civilizations in the galaxy. If the chemical prerequisites for life are distributed throughout the galaxy by interstellar objects, then the probability of life arising on suitable worlds might be much higher than previously calculated. The timeline for life's emergence might also be accelerated. Rather than waiting millions of years for suitable chemistry to develop locally, planets might begin the process of abiogenesis, the transition from chemistry to biology, shortly after forming, aided by the complex molecular inventory delivered by interstellar visitors. Dr. David Deamer of the University of California, who studies the origin of life, found the implications exciting but cautioned against premature conclusions. We're still learning about the conditions required for life to begin, he observed, but the possibility that interstellar objects contribute essential chemistry to this process adds a new dimension to our understanding of how life might arise throughout the universe. As observations of Atlas continued, astronomers found themselves not just studying an astronomical phenomenon, but potentially witnessing one of the universe's most important biological processes, the seeding of star systems with the chemical and perhaps biological materials necessary for life to flourish. Each molecule released into space carried with it the potential to participate in the emergence of new forms of life around distant stars. In the chaotic early phases of stellar birth, when massive stars ignite within dense clusters of their siblings, gravitational forces operate on scales that can reshape entire regions of the galaxy. It is during these violent episodes that some of the universe's most consequential processes unfold, including the capture of interstellar objects that may determine the fate of future planetary systems. Dr. Suzanne Falsner's team at the Max Planck Institute for Radio Astronomy used sophisticated computer simulations to model what happens when high-mass stars, those more than 8 times the mass of our Sun, form within stellar clusters. Their results revealed a process of cosmic piracy operating on an almost unimaginable scale. As these massive stars condense from their parent molecular clouds, their powerful gravitational fields reach out across light years of space, capturing any interstellar objects that happen to be passing through the region. The simulations showed that a single high-mass star could capture millions of such objects during its formation phase, incorporating them into the disk of gas and dust from which planets would eventually form. We're talking about a process that operates like a cosmic vacuum cleaner, Falsner explained during a presentation at the European Planetary Science Congress. These massive stars sweep up interstellar objects from across huge volumes of space, concentrating them into their protoplanetary disks, where they can participate in planet formation. The captured objects don't simply fall into the star and disappear. Instead, they settle into stable orbits within the protoplanetary disk, distributed across a range of distances from the central star. Computer models showed that these objects could survive for millions of years within the disk environment, gradually accumulating additional material until they grew into the cores of new planets. This process solved several long-standing puzzles in planetary formation theory. The diversity of planetary compositions observed in exoplanet surveys had been difficult to explain if planets formed only from the materials present in their local protoplanetary disks. But if planetary systems incorporated materials captured from across interstellar space, the observed chemical diversity became not just explainable, but expected. The implications extended to our own solar system's history. Our Sun formed within a stellar cluster about 4.6 billion years ago, and the conditions during that formation phase might have been ideal for capturing interstellar objects. Some of the asteroids and comets now orbiting our Sun might actually be refugees from other star systems, captured during the chaotic early phases of solar system formation. This possibility offered new perspectives on some of the anomalous objects found in our outer solar system. The unusual orbit of the dwarf planet Sedna, the strange composition of some Kuiper belt objects, and the peculiar characteristics of certain comet families might all reflect the influence of captured interstellar material. The capture process also provided a mechanism for the rapid formation of gas giant planets. Traditional models struggled to explain how objects like Jupiter could accumulate massive atmospheres before the protoplanetary disk dissipated. But if these planets formed around captured interstellar cores that were already substantial in size, they could begin accumulating gas immediately, solving the timing problem that had puzzled astronomers. Even more intriguingly, the captured objects might carry with them the chemical signatures of their birth environments. Planets that formed around such cores would inherit trace elements and isotopic ratios that reflected conditions in other star systems. This chemical memory might preserve information about galactic chemical evolution, creating a fossil record of stellar nucleosynthesis spanning billions of years. The research also suggested that the effectiveness of the capture process might vary depending on the stellar environment. Stars that formed in dense clusters might capture more interstellar objects than those that formed in isolation. This could lead to systematic differences in planetary system architecture and composition, depending on the stellar formation environment. As Atlas streamed through our solar system, releasing its cargo of water and organic compounds, it might have been demonstrating the same process that helped form our own worlds billions of years ago. The materials now escaping into space might someday be captured by forming star systems elsewhere in the galaxy, participating in the birth of future planets around distant suns. The capture of worlds thus emerged not as a rare or exotic process, but as a fundamental mechanism by which the universe distributes materials for planet formation across galactic distances. Every star system becomes both a contributor to and a beneficiary of this cosmic exchange, ensuring that the chemical diversity necessary for complex planetary systems is available wherever new worlds form. As astronomers piece together the evidence from Oumuamua Borisov and now 3I Atlas, a grand narrative begins to emerge, one that connects the formation of our own solar system to the birth of worlds throughout the galaxy in an unbroken chain of cosmic creation. Each interstellar visitor represents not just a curious anomaly, but a link in a process that may be fundamental to how the universe creates complexity and life. The story begins in the earliest epochs of galactic history, when the first generation of massive stars forged heavy elements in their nuclear furnaces and distributed them throughout space in spectacular supernova explosions. These stellar death throes seeded the galaxy with carbon, oxygen, silicon, and iron, the raw materials from which rocky planets and complex chemistry would eventually emerge. But the distribution of these elements was far from uniform. Different regions of the galaxy experienced different rates of star formation, different patterns of stellar death, and different histories of chemical enrichment. The result was a patchwork of environments, each with its own unique chemical signature that would be inherited by the planets and smaller bodies that formed within them. As subsequent generations of stars formed from this chemically enriched material, they incorporated the diverse elements into their protoplanetary disks. Some systems formed in regions rich in carbon and organic compounds. Others developed in environments dominated by water ice and silicate minerals. Still others emerged in zones where rare elements and exotic compounds were more abundant. Dr. Brad Gibson of the University of Hull, who studies galactic chemical evolution, described this process as cosmic heredity. Each star system inherits the chemical legacy of all the previous generations of stars that contributed to its formation region. But unlike biological heredity, which passes information only from parent to offspring, cosmic heredity operates through a complex network of exchanges that connect all regions of the galaxy. When gravitational interactions eject objects from these chemically diverse systems, they become carriers of their birth environment's unique chemical signature. A planetesimal ejected from a carbon-rich system carries organic compounds and complex hydrocarbons. An object from a water-rich environment like Atlas transports ice and the organic chemistry that can develop in aqueous environments. Each becomes a messenger carrying samples of its parent system's chemical heritage across interstellar space. These messengers don't travel in isolation. Computer simulations suggest that the galaxy may contain trillions of interstellar objects at any given time, creating a vast network of chemical exchange that operates on timescales of millions to billions of years. Objects ejected from one system travel through space for eons before being captured by newly forming systems, where they contribute their chemical cargo to the formation of new worlds. The process operates like a cosmic library system, where each star system both contributes books to the collection and borrows volumes from elsewhere. Over billions of years, this exchange ensures that the chemical knowledge accumulated throughout the galaxy becomes available to every new generation of planetary systems. Our own solar system appears to be both a contributor to and beneficiary of this process. The objects now in our Kuiper Belt and Oort cloud represent our system's contribution to the interstellar population, frozen repositories of early solar system chemistry that may someday seed worlds around other stars. Meanwhile, visitors like Atlas demonstrate that our system continues to receive contributions from elsewhere in the galaxy. The implications for planetary habitability are profound. Rather than depending solely on the chemical lottery of their local formation environment, worlds throughout the galaxy may benefit from the accumulated chemical wisdom of billions of years of stellar evolution. The complex organic compounds necessary for life need not arise independently in each system, but can be distributed through the interstellar messenger service operated by wandering objects like Atlas. This perspective transforms the search for life from a hunt for rare chemical coincidences to an exploration of a galaxy-wide process of chemical evolution and distribution. Life may not arise in isolated pockets of suitable chemistry, but through a connected process that links the emergence of complexity throughout the galaxy. As Atlas continues its journey through our solar system, it serves as a visible reminder of these deep connections. The water molecules it releases carry chemical information from across the galaxy and across cosmic time. Some may eventually be incorporated into future worlds, contributing to atmospheres and oceans that have not yet formed around stars not yet born. Beneath the apparent emptiness of interstellar space lies a hidden infrastructure, a vast network of wandering objects that connect every star system in the galaxy through subtle but persistent exchanges of matter, chemistry, and information. The passage of 3I Atlas through our solar system offers a glimpse into this cosmic network, revealing the universe as a far more interconnected and dynamic environment than our ancestors ever imagined. The scale of this network defies easy comprehension. Conservative estimates suggest that our galaxy contains more than 1 trillion interstellar objects, larger than 1 kilometer in diameter, with countless smaller fragments filling the spaces between. These objects follow complex orbital paths that wind through the galaxy over millions of years, occasionally intersecting with star systems to deliver their chemical cargo before continuing their cosmic journeys. Dr. Robert Warwick, whose team at the University of Western Ontario specializes in detecting small solar system bodies, has calculated that interstellar objects may pass through our solar system several times per year. Most are too small or too distant to detect with current technology, but they represent a constant stream of visitors from other worlds, each carrying samples of alien chemistry. We're beginning to realize that our solar system exists within a kind of cosmic ecosystem, Warwick explained. Just as Earth's biosphere depends on the continuous cycling of nutrients between different environmental compartments, star systems throughout the galaxy participate in the cycling of chemical elements and compounds on much larger scales. This cycling operates through multiple mechanisms simultaneously. Gravitational encounters between stars can disrupt the outer regions of planetary systems, sending comets and asteroids on trajectories that carry them to other systems. Stellar winds and radiation pressure can accelerate smaller particles to interstellar velocities. Even the galaxy's rotation creates differential motions that gradually redistribute materials across vast distances. The network shows evidence of organization and structure. Computer simulations reveal that interstellar objects don't wander randomly through space, but follow preferred pathways determined by the galaxy's gravitational architecture. Dense stellar clusters serve as redistribution hubs where objects from many different systems can be exchanged. Spiral arms act as collection and concentration zones, where the probability of interstellar encounters increases. Some researchers have begun to explore whether this network might serve functions beyond simple chemical exchange. Dr. Gregory Laughlin of Yale University has proposed that interstellar objects might carry more than just passive chemistry. They might transport information in the form of complex molecular arrangements or even biological materials preserved in their icy matrices. If we think of interstellar objects as carrying molecular libraries from their birth systems, Laughlin suggested, then the galaxy begins to look less like a collection of isolated worlds and more like a vast information processing system. Each interstellar encounter becomes an opportunity for systems to share not just materials, but the molecular knowledge accumulated through billions of years of chemical and potentially biological evolution. This information-sharing process might operate on multiple levels simultaneously. At the simplest level, the isotopic ratios and chemical compositions of interstellar objects provide information about stellar nucleosynthesis and planetary formation processes in their parent systems. More complex organic molecules might carry information about atmospheric chemistry, surface processes, and environmental conditions on ancient worlds. At the most speculative level, some researchers wonder whether interstellar objects might preserve and transport biological information across cosmic distances. If life is more resilient than previously thought, and if interstellar objects can maintain suitable conditions for biological preservation during their long journeys, then the network might serve as a galaxy-wide mechanism for biological exchange. The arrival of Atlas with its rich inventory of water and organic compounds provides a case study in how this network operates. The object's composition reveals information about chemical processes that operated in its birth system millions of years ago. Its current activity demonstrates how interstellar objects can remain chemically active even after eons of travel through the cold vacuum of space. As Atlas releases its cargo into our solar system, it's participating in the network's primary function, the redistribution of chemical complexity throughout the galaxy. Some of the molecules now escaping from its surface will be captured by our planets and moons, becoming part of our system's chemical inventory. Others will eventually escape our system entirely, joining the interstellar medium to await incorporation into future worlds. This process ensures that chemical innovations developed in one corner of the galaxy can eventually benefit worlds throughout the entire galactic community. The network serves as both a preservation system, maintaining chemical diversity against the entropy of cosmic evolution, and a distribution system, ensuring that the materials necessary for complexity and life remain available wherever conditions permit their use. In the profound silence of space where sound cannot travel and words have no meaning, the universe has developed its own language, one written in the motion of particles, the emission of light, and the gravitational dance of matter across cosmic distances. As 3i Atlas streams through our solar system, it speaks to us in this ancient tongue, telling stories of worlds we will never see and chemical processes we can barely imagine. The language consists not of words or symbols, but of physical phenomena that carry information across the vast emptiness between stars. Every photon emitted by Atlas encodes data about the temperatures, pressures, and chemical compositions that existed in its birth system. Every molecule of water vapor released into space carries isotopic signatures that record the nuclear history of its parent star. Every gravitational perturbation reveals information about the object's mass, density, and internal structure. Dr. Alan Boss of the Carnegie Institution for Science, who studies the formation of planetary systems, describes this cosmic communication as physics as poetry. The same fundamental forces that govern the behavior of atoms and planets also serve as carriers of information, creating a universe where every process simultaneously performs its immediate function and broadcasts data about the conditions under which it occurs. The vocabulary of this cosmic language is written in the periodic table of elements. Each chemical species has its own spectroscopic signature, its own pattern of emission and absorption lines that serve as an identification card readable by any sufficiently sensitive instrument. When Atlas releases hydroxyl radicals into space, it's essentially broadcasting the message water is present, in a frequency that telescopes throughout the galaxy could detect and understand. But the language goes deeper than simple chemical identification. The relative abundances of different isotopes tell stories about stellar nucleosynthesis, the nuclear processes that created heavy elements in the cores of massive stars. The ratios of different chemical species reveal information about the temperature and pressure conditions under which they formed. Even the patterns of molecular rotation and vibration carry information about the physical environment in which the molecules exist. This information flows freely throughout the galaxy, carried by light waves, charged particles, and wandering objects like Atlas. Every star system continuously broadcasts its chemical signature into the cosmic environment, creating a vast library of information about the conditions and processes operating throughout the galaxy. Any civilization with sufficiently advanced instruments could, in principle, decode this information to learn about conditions on worlds they will never visit. The passage of interstellar objects adds another dimension to this cosmic communication. While light carries information instantaneously across interstellar distances, it provides only a snapshot of conditions at the moment of emission. Interstellar objects, by contrast, carry preserved samples of ancient chemistry that can be analyzed in detail when they encounter other star systems. In this sense, objects like Atlas serve as time capsules, preserving chemical information from their birth environments and delivering it intact after millions of years of travel. The water now streaming from its surface carries molecular memories of conditions that existed in an alien star system when our own solar system was young. Every hydroxyl radical glowing in our sun's ultraviolet light is a messenger from the deep past of another world. The implications for communication and discovery are profound. If advanced civilizations exist elsewhere in the galaxy, they might use this natural information-carrying capacity of interstellar objects to send messages across cosmic distances. Rather than broadcasting radio signals that fade with distance, They might encode information in the chemical compositions or orbital characteristics of objects ejected from their systems. Even without deliberate communication, the natural flow of information through interstellar objects provides a mechanism for civilizations to learn about each other indirectly. The chemical signatures of industrial activity, the isotopic ratios produced by nuclear technology, or the molecular complexities associated with biological processes might all be detectable in the compositions of interstellar visitors. As astronomers continue to study Atlas and future interstellar objects, they're essentially learning to read the universe's natural language with increasing fluency. Each new detection adds vocabulary to our cosmic dictionary. Each spectroscopic analysis reveals new grammatical structures in the physics of matter and energy. The universe, it seems, is not silent after all. It speaks constantly in the language of chemistry and physics, telling stories of stellar birth and death, planetary formation and destruction, and the endless cycling of matter and energy that connects all worlds in a vast, ongoing conversation that spans the galaxy and reaches across cosmic time. For most of human history, we have looked up at the night sky and seen isolation. The spaces between stars appeared empty, vast voids that separated our world from any others that might exist in the cosmic darkness. This perception shaped our understanding of Earth's place in the universe, a lonely island of life floating in an ocean of nothingness, connected to the cosmos only by the light of distant suns. The discovery of interstellar objects like 3I Atlas is rewriting this narrative in fundamental ways. What we once perceived as empty space is revealing itself to be filled with wandering worlds, each carrying chemical messages between star systems and participating in a galaxy-wide process of material exchange that has been operating for billions of years. Dr. Avi Loeb, reflecting on the rapid succession of interstellar discoveries, noted the paradigm shift occurring in astronomy. We're realizing that we've been looking at the galaxy through the wrong lens. Instead of isolated star systems separated by empty space, we're seeing evidence of a connected network where materials, chemistry, and potentially even life flow freely between worlds. The implications of this realization extend far beyond astronomy. If the space between stars is filled with objects carrying complex chemistry from one system to another, then the traditional concepts of planetary isolation and chemical scarcity may need fundamental revision. Worlds throughout the galaxy may be far more connected than we ever imagined, participating in a cosmic ecosystem that operates on scales of time and distance that dwarf human experience. Consider what this means for our understanding of life's origins on Earth. Traditional theories assume that life arose from chemical processes operating within our solar system's isolated environment. But if interstellar objects regularly delivered complex organic compounds to the early Earth, then life's emergence might have been aided by chemical contributions from across the galaxy. The molecules that first organized themselves into self-replicating systems might have carried information and structural patterns developed on worlds we will never know. The concept transforms our perspective on the search for life elsewhere in the universe. Rather than looking for rare chemical coincidences that might produce life independently in isolated systems, we might be searching for manifestations of a galaxy-wide process of chemical and biological evolution. Life might not arise in isolated pockets, but through connected processes that link the emergence of complexity throughout the cosmic community. Even our understanding of planetary formation requires revision. The traditional model assumes that worlds form from the materials present in their local protoplanetary disks. But if forming systems regularly capture interstellar objects, then planets throughout the galaxy might incorporate materials and chemistry from multiple star systems. The diversity of exoplanets detected by space-based telescopes might reflect not just local variations in disk composition, but the accumulated contributions of interstellar messengers captured during planetary formation. The timeline of cosmic evolution also takes on new significance. Processes that we thought required billions of years of local development might be accelerated by contributions from other systems. Complex chemistry, organic compounds, and potentially even biological materials might spread throughout the galaxy much more rapidly than previously thought possible. Dr. Sarah Seeger, whose work focuses on the potential for life on exoplanets, sees these discoveries as opening new avenues for astrobiology research. If interstellar objects can preserve and transport complex chemistry across cosmic distances, we need to expand our thinking about how and where life might emerge. The galaxy might be a much more biologically connected environment than we've assumed. The philosophical implications are equally profound. Humanity's sense of cosmic isolation, already challenged by the discovery of exoplanets and the vastness of the universe, faces further revision. We may not be alone on an isolated world, but part of a galactic community connected by ancient processes of chemical and potentially biological exchange. As Atlas continues its journey through our solar system, releasing water molecules that will become part of our local environment, it serves as a tangible reminder of these deep connections. The cosmic network that we're only beginning to understand has been operating throughout the galaxy's history, silently connecting worlds and distributing the materials necessary for complexity and life. What we've been missing is not just a few unusual objects wandering through space, but evidence of the universe's greatest achievement: the creation of a system that connects all worlds in a vast network of chemical and potentially biological exchange that transcends the boundaries between star systems and links the emergence of life throughout the galaxy. As our journey through the story of 3i Atlas draws to a close, the interstellar visitor continues its ancient voyage through the outer reaches of our solar system. Its moment of greatest activity has passed, the dramatic water emissions that first captured our attention now diminishing as it travels farther from the sun's warmth. Soon it will fade from our telescope's view, becoming once again a distant speck of light carrying its remaining secrets back into the cosmic darkness from which it emerged. But the silence that follows its departure is not empty. It is filled with the profound implications of what we have witnessed, evidence of connections that link our world to the farthest reaches of the galaxy, processes that operate on scales of space and time that humble human imagination, and possibilities that challenge our most fundamental assumptions about life's place in the universe. The water molecules that streamed from Atlas during its passage through our solar system have begun new chapters in their cosmic journey. Some have been captured by the atmospheres of Mars and the outer planets, joining the chemical inventory of worlds that may someday harbor life. Others continue outward, joining the thin material between stars to await capture by future planetary systems around suns not yet born. In the laboratory and observatory, astronomers continue to analyze the data collected during Atlas's visit. Each spectrum contains information that will take years to fully decode, each observation revealing new details about the chemistry and physics of interstellar objects. The scientific papers describing these discoveries will join a growing literature that is rewriting our understanding of the galaxy as a connected, dynamic environment rather than a collection of isolated worlds. But perhaps the most significant legacy of Atlas lies not in the data it provided, but in the questions it raised. If interstellar objects regularly carry complex chemistry between star systems, what other processes might be operating on galactic scales that we have not yet recognized? If the materials of worlds flow freely throughout the cosmic community, what does this mean for our understanding of life's emergence and distribution? Dr. Dennis Bodowitz, whose team first detected Atlas's remarkable water emissions, often reflects on the broader significance of their discovery. We set out to study a single interstellar object, but what we found was evidence of processes that connect all worlds throughout the galaxy. Atlas showed us that we're not observers of the universe, but participants in its greatest story, the continuous creation and distribution of complexity that may ultimately lead to life throughout the cosmos. The green luminescence that first marked Atlas as unusual has faded now, its diatomic carbon emissions dimming as the object moves beyond the reach of intense solar radiation. But the glow it cast on our understanding of the universe continues to illuminate new pathways for research and discovery. Future missions to intercept interstellar objects are already being planned. Telescopes designed to detect even fainter visitors are under development, and theories about galactic-scale processes are being refined and tested. As Atlas disappears into the constellation Lynx, following a trajectory that will carry it back into interstellar space, it leaves behind more than just scientific data. It leaves a transformed perspective on our place in the cosmos. We are not alone on an isolated world, but citizens of a galaxy where the materials of life flow freely between star systems, where the chemistry of ancient worlds contributes to the birth of new ones and where the boundaries between systems dissolve into a vast network of exchange and connection. The universe, we have learned, is not a collection of separate worlds but a single vast ecosystem in which every star system participates in the cosmic community through the silent wandering of messengers like Atlas. These interstellar travelers carry with them not just chemistry and physics, but the accumulated wisdom of billions of years of stellar evolution, the molecular memories of worlds that have lived and died, and perhaps the seeds of life itself. In the end, the story of 3i Atlas is not just about a single visitor from another star. It is about the recognition that we live in a universe where worlds are connected across impossible distances, where the emergence of life may be a collaborative process involving the contributions of countless systems, and where every molecule of water that falls as rain carries within it the chemical heritage of stars. As we continue to watch the skies for future interstellar visitors, we do so with the knowledge that each one carries messages from across the galaxy, participating in the universe's greatest experiment, the continuous seeding of worlds with the materials and information necessary for complexity chemistry, and perhaps life itself, to flourish throughout the cosmic community. If you found yourself drawn into this cosmic story, consider joining us on future journeys as we continue to decode the messages carried by these wandering messengers from other worlds. The universe has many more stories to tell, and each interstellar visitor brings us closer to understanding our true place in the vast community of worlds that spans the galaxy. This complete documentary script maintains the calm, cinematic tone throughout, while building a comprehensive narrative about 3i Atlas and its implications for our understanding of the universe. Each chapter flows seamlessly into the next, creating a single, continuous story suitable for voiceover narration.